Pretty well already. So, like I said earlier, if you have questions, just jump in with them and ask them out loud. But this is going to be balancing chemical equations. And apologies to DeAndre, because I know you've seen this before. Well, when we are marking things out, we tend to get kind of a recipe, a guide for what goes together. And you'll see you have chemical species 1, and then you'll get chemical species 2. And when you mix them together, some amount of chemical species 3 is going to come out. And it's just saying, like, if you mix together 1 part, in this case, it's 1 part nitrogen gas and 3 parts hydrogen gas, you're going to get 2 parts of ammonia gas. So it really is a recipe. It's just like baking. And instead of saying part, because it's chemistry, we use the term mole, but it's not like 1 cup of this and 1 cup of that. It is moles that we are relating to each other. So that's one of the key takeaways of all of this, and it gets really confusing until you kind of get the mole concept in your head. You don't have to worry about the giant string of numbers for how much is in a mole. We just say, you know, we've got 1 mole. And I think about all of this like food. Did you guys all eat lunch?
I didn't.
Oh, you're going to be so hungry by the time we're done with this, man.
I just had body conditioning as well. I was going to make a whole thing of pasta when I was done.
Well, I think about this. This is the most boring ham sandwich recipe, but it makes an easy analogy. You have 2 pieces of bread and 1 piece of ham, and that makes 1 sandwich, right? Very boring sandwich. So when we're using stoichiometry and kind of this balancing chemical equations idea, we want to compare any 2 of the substances in the recipe at any given time. So we want to say, how many sandwiches can I prepare if I have 12 pieces of bread? Somebody jump in. 6. How much bread is needed to use up 8 slices of ham?
16.
Good. And if I only have 4 slices of ham in my fridge, how many sandwiches can I make?
4 if you have them.
That was easy, right? Why was the homework hard? Now, it does get more complicated than that, and you guys are too young. There used to be this song with about how to make a Big Mac, but like if you are doing stuff in a fast food restaurant, they have a recipe that you follow, and this would be like a really involved, but still a recipe for making like a Big Mac. Well, a hamburger in this case. You have a patty, 2 slices of cheese, 2 tomatoes, 1 full bun, 3 packets worth of ketchup, 5 pickles, and a thing of lettuce. And then you got to put it all together. But the same logic still applies. So how many ketchup packages would we need to make 12 cheeseburger?
36.
All right, you got to enunciate a little bit better though.
36.
Awesome. Now somebody else, how many slices of cheese would you need to make 8?
16.
Yeah. And there's nothing wrong with like counting on your fingers if you feel like you need it. And what is the ratio of lettuce to tomato slices?
1 to 2.
Yeah, so you can say we have 1 piece of lettuce for every 2 slices of tomato. And that's a little bit more chemical thinking on it. And if we're using chemistry terminology, what are the reactants for this chemical equation?
Everything?
So everything up to the cheeseburger is going to be a reactant. And this is something that they'll just drop in questions all the time, but reactants is kind of the left-hand side of the arrow. But it's everything that's going into what we're making. Products is going to be the stuff at the very end. It is kind of easy though, like products is what comes out, reactants are what go in. So now we got to talk about our chemical coefficients. We all know what coefficients are in algebra. So the coefficients in our chemical reaction are representing the ratio of molecules, of individual units that react. But since it's the ratio of individual units, that also is the ratio of moles, since moles is just a giant dozen. So when we think about it, it's back to that, how many sandwiches can I prepare with 12 slices of bread? We're going to do this ratio math, and when we do it longhand, it's very tedious feeling. So if we have 12 bread, and we know that our ratio is, you have how many sandwiches and then how much bread. And this is how we're setting up the problem so that we can cancel out bread in each location and just get sandwich. So this should look a little familiar. And we're just pulling the numbers from where they're coming from in our chemical equation here. Now, Zane did that in his head so fast it was boring, right? Yeah. And we can all do that in our head. When we look at it chemical equation wise, this is one of the parts that just freaks everybody out. And so you want to, you get the number from the ingredients list or the product itself. And then you just do the silliest algebra you've ever done. Cancel out bread. 12 multiplied by 1 over 2 is 6. Super easy. Then our other thing, we got our 8 slices of ham, the long version, 8 ham times, and then we have to stick ham on the bottom and we stick bread on top. And that's a 2-to-1 ratio. Cancel out your units, and it just becomes 8 times 2 bread is your answer. Okay, this is actually the most boring one that we ever do. But do you have any questions about the way we set up these particular problems? No, we're good so far? So we call this part the mole ratio conversion step, which is a mouthful. But you'll hear the ratio of which one to which one, that is your mole ratio. And if you use a mole ratio conversion step, that is how we end up comparing apples to oranges in a very real way in chemistry. So now I got to go back to the ammonia thing. More real chemistry, less sandwiches. Got our chemical formula right there. Now, how many moles of ammonia can be produced by the complete reaction of 4 moles of nitrogen? Now, you guys know I live in these awkward silences. This is my happy place, but do you have an answer?
4.
I could barely hear that.
Would it be 4?
So we have 4 moles of nitrogen. correct? So now how many moles of ammonia can we make? Oh, you got to speak up, man. It's being recorded for the voice, but not the text or the pictures.
8.
So we've got 4 and we've got 8. Guess what we're going to do? We're going to set up the problem. So what is our ratio of nitrogen gas to ammonia in the chemical formula? You just pull the number down and you make sure that you have whatever you start with. You want to set the thing that you're going to cancel out on bottom. So that same unit here is going to go on bottom for the problem. So that's 1 mole of nitrogen to 2 moles of ammonia. That's our mole conversion step. And as it pops out, we've got 8 moles. I don't know why when it's food, it's easy, but when it's chemistry, our brains take a left-hand turn.
Okay, wait. So is NH ammonia?
NH3 is ammonia.
Okay.
Don't worry about that. I mean, it doesn't matter what the chemical is called. It's just you find you have this thingy here and you're looking for it right there. Now that coefficient is the number directly in front. So in this recipe, it's 1 unit of nitrogen to 3 units of hydrogen is going to make 2 units of ammonia. Yeah, it's
Okay.
like the sandwich.
I understand now. Okay. Thank you.
And it will always, when you look at it with those weird letters and numbers and like this G in parentheses, I mean, that's all correct in there. Does it matter? No. I mean, this is saying we're making gases out of gases, but for the math part, it is easy enough to ignore. I've got another example. How many moles of nitrogen are needed to react completely with 6 moles of hydrogen gas?
Two.
Two.
We do the same setup every single time. Write out what you're given. Then I'm going to find the number that's in front of that hydrogen and stick it on bottom, because that's what we got to cancel out. Nitrogen is the target unit, so I'm going to stick that on top. That's our mole ratio conversion step. Cancel everything, do simple math, and we get a nice, easy answer. Now I'm going to be straight with you guys on this. You will, in real life chemistry, it tends to be kind of simple, especially the stuff that we'll be doing when we get into the lab. On any test, instead of making it simple and then giving you a multiple guess thing, people make them hard. They make them hard to make sure that you have the concept, but also they will try to trip you up and make you doubt yourself. If you looked at that and you thought too, and then you kind of hung out for a second and waited to say something, that's a normal human reaction. But it really was that easy. You've got it. Now, this is another, I have a lot of fun analogies, but if I have the shells of cars, let's assume they have all the working bits, and I have a pile of car tires. Maybe I'm starting a NASCAR team. How many cars can I make? Like, I have 8 car bodies. I have 48 tires. That's enough tires, right? Now, I've got all these guys left over all of a sudden. This is what we call a limiting reactant, in that I have an extra amount of tires, so my total amount of product is going to be determined by how many car bodies I had in that situation. If I was thinking about an equation that would write it out, instead of having to draw a bajillion cars, I would have, I got car bodies plus 4 tires is going to give me a car tire 4. I mean, this is a goofy way to try to write this out, I realize. But this is exactly analogous to methane. You guys know methane gas? Where does methane come from?
Cows.
Like they breathe it out?
Farting.
Out of the back end.
Isn't that fun to say? You should all say cow farts. It's super fun. So when we get carbon atoms and we get hydrogen molecules, because the hydrogens are all teamed up, they're in little teams of 2. So they're a molecule, not just an atom. We will get methane as a result when you mix them together. This is the exact number that we had of cars and tires. And so it's a really analogous concept. Now, it didn't quite fit on the PowerPoint conversion. Our math for it would be 1 carbon atom plus 2 hydrogen molecules, that's 2H2, is going to give us CH4. This is where it starts getting a little tricky. This little 2. It means that our hydrogens are in teams of 2. That part makes sense, right? So you got 1 and then another one that you need to kind of pop over here. Boop, 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 and the last one, boop, to make it work out. The number in front you can think of as a multiplication. So this is saying 4 H's total. Yeah, so if you have a little subscript, I mean, that's just saying they're stuck together. And in this case, because all of the letters are run together, that's CH4. They're all glued together. They live as a happy little methane molecule. You're going to get a lot of visualization like this as well. The Zoom doll people here do the AP Chemistry textbook that I like to use. But when you look at the containers, you've kind of got stuff floating around, and you can draw a line in your head to kind of corral stuff. And these are our hydrogens and our nitrogens, again making ammonia, NH3. It's one of the kind of easy sample molecules that we work with. So it's going to take, you've got 1 nitrogen molecule and 3 hydrogen molecules, and that makes 2 ammonia molecules in the end. And in these jars, everything has combined. So it's an even amount, and then everything can come together. Things are rarely even in real life. I'll tell you that most of the air we breathe is N2. It doesn't really do anything for us, just goes in and out. Getting H2 is much more difficult. So if you were going to be, say, making ammonia on a massive scale, you care about the H2s that you can collect. Now in this container, do I have enough nitrogen to use up all the hydrogen? And it's okay to count on your fingers as you look at it. And maybe the converse, do I have enough hydrogen to use up all the nitrogen? So when I combine these guys, what do I have left over?
Two hydrogen. No, two nitrogen. Okay,
So you think we have enough hydrogen to use all, but like when you say two, do you mean two or two?
two molecules.
Two molecules, cool. Yeah, and this is like always using units. So there we are. That's just kind of circling everything for us. And you will generally find that using pictures, which is something they will give you on the AP exam, and I'll always give you, is one way of approaching it, and you may do better with that. You may actually not do better with pictures and do better with math. You'll get both kinds of questions, so you'll have to practice the bad one. I find visualizing very appealing, but if I have to draw everything out, my drawing is so terrible. I felt bad for whoever had to grade my papers back in the day. And these are not going to line up properly because I made it too small. Ugh. The terminology that we have here is if you have extra stuff, that is excess. And if there's something that limits the total progress, that is limiting. So we have excess and limiting reactants. And down at the bottom, your limiting reactant determines how much product you can get out of something. And this is a huge concern for any industrial or commercial chemistry operation, is how much you can make with the ingredients that you have. Now, real world limiting reactants, iron and sulfur go together. They make something, I mean, iron sulfide is what you would say out loud, but in real life, we call that fool's gold. I'm interested in making fool's gold so I can sell it to some fools at the gem show. Now, in the first set, we have a perfect lineup. What about in the second set? What do I need to go get? What is my limiting reactant? So what do I need to get to make more fool's gold?
Iron.
Yeah, so Fe is iron. Anybody speak Spanish? No? Anybody speak Latin?
I speak Spanish.
Oh, ¿cómo se dice iron en español?
That one I don't know.
Hierro.
Fierro, yeah. So you're going to get a lot of the older terms are either Latin or Greek based. So the Fe is a Latin word. Ferris or ferros was what it was in Latin. And just if you speak Spanish, it makes a ton of sense. There's one element I know of that's a German name, but we can't explain them. But yeah, see there, I had not enough iron, so my excess was sulfur in that case. I know, I told you you'd be hungry after this. So thinking about this, now making it a better chemical, I'm writing 2B plus C is going to make us B2C. How do we feel about the change between our coefficient and the little dangly bits there? All right. So I am making a bunch of sandwiches. I got 100 pieces of bread, 30 slices of cheese. How many sandwiches can I make?
$30.
Yeah, easy math, right? As soon as it's food, it's easy. You didn't even need the multiple guess. So many grilled cheese sandwiches. Then think, if I have 4 slices of bread, an entire jar of peanut butter, and half a jar of jelly. The obvious limiting reactant in that case is bread. I can't stick an entire jar of peanut butter in between 4 slices of bread. I mean, I could, but then it would fall all over the plate. And your excess is your peanut butter and jelly. And this is just review of the concepts. I say them a lot, so if you hear it 3 times, make sure you have it written down once. But your limiting reactant is completely used up, determines the amount of the product. Your excess reactant, in real life, you usually get the cheapest ingredient for a chemical process, like nitrogen gas for that ammonia making stuff. You add extra excess reactant to completely use up the expensive stuff so that you make the most product you can. And the excess reactants are generally cheaper and oftentimes also easier to recycle. Oh man, this is going to drive me crazy. So when we're thinking about a Big Mac, you have 2 pieces of meat, 3 pieces of bread, and just all your condiments. We're calling that everything else. And it comes out as Big Mac. So if you have 30 pieces of meat and excess of everything else, how many Big Macs can you make? Since you have 2 meats to 1 Big Mac, you just are dividing that guy by 2, or realistically multiplying by 1/2. What if I've got 30 pieces of bread and everything else is in excess? How many Big Macs can I make? Now, if I have 30 meat and 30 bread, how many Big Macs can I make?
10.
So we're again limited by whichever one is going to produce the absolute least. In this case, when you look at the 30 meat and 30 bread side by side, 30 meat's going to yield more. You can also just look at your equation at the top and realize which one gets used up at a much faster rate. And you can even think about this. We've got this tricycle concept. You've got 3 wheels, 2 pedals, a seat, a handlebar, and a frame. So it gets really complicated. Well, complicated looking, right? But the same logic will apply no matter how complicated it gets. If I've got 50 pedals, then how many tricycles can I make?
25.
25.
Yeah, 25. So this is starting to get easy, right? $50 seats, it's going to make 50. That's an easy 1-to-1. And then the same thing as with the Big Mac example, if you've got 50 pedals and 50 seats, you look at which one will result in the lowest number, and it will make only those. I will have bought way too many seats, and my boss at the tricycle shop will fire me. So that's the start of just kind of looking at chemical equations and how the balanced chemical equation works for us. Now, what questions do you guys have for me about that?